I attended a lecture by Dragomir Anguelov. He's head of research at Waymo, and he gave an overview over what Waymo is doing, and I thought it was amazing. Shout out to Dragomir, shout out to Stanford to enable these types of lectures is just amazing. So I'm going to go over what Waymo is doing. I think the big picture here is I'm going to talk about what they've been doing so far, and then also what the sort of outlook is in terms of what the future is going to look like. So fundamentally, I think most interesting, he was talking about Waymax, which is the simulator for multi-agent behavior in traffic. So we're talking about simulation here. Then a lot about motion planning. I mean, that's obviously one of the fundamental problems in autonomous driving is still perception, and then planning in terms of motion is, okay, what do I see, and the things that I see, are they going to move, and if so, in what direction, and so on and so forth. And then what's the interplay also? Multi-agent motion planning. There's definitely a lot of that. Or auto-labeling infrastructure. This is obviously it's part of the infrastructure, and the more you have, the more ideas you have. And the reason auto-labeling is important, and it's going to get to the future projects, but think about it this way, like, yes, you can probably do an end-to-end learning mechanism where maybe you don't have to label anything, but if you could label, let's say there's a car flipped on its back and in the middle of the road because of an accident, if you could maybe use an LLM to semantically organize the scene, you can just reduce the search space in a sense, and that's where I personally think auto-labeling still has a future. Model distillation is the idea that you have a large model and then you try to distill whatever that model does in a smaller model, so you can run it with a lower compute budget. Future projects, they're all kind of in sort of the transformer space, which makes sense where we are. So vision language models, architectures optimized for video and other modalities, scene description formats, reconcile concurrent scenes description with LLM scene, language conditional planners, follow human instructions, preserve LLM capabilities, limit the compute budget. So these are, I think, what Waymo is working on, according to Drago, in currently and in the future, and maybe what researchers should be taking away from here is we're trying to incorporate transformer technology wherever we can, because it's so powerful and it generalizes really fast. This is the part 8 of the series of foundation models for embodied decision-making agents. It's also part of the event discussion. This was an event at Stanford, but I'm going to still put it in the category embodied decision-making agents, because I believe this is a lot more relevant to the actual research that we're doing in robotics, and directly related, of course, to Tesla. So the first idea I want to talk about is Waymax. So this is an accelerate data-driven simulator for large-scale autonomous driving research. So the idea here is that you have a simulator that looks at traffic scenarios and simulates realistic traffic scenarios. The idea here fundamentally is generation of diverse scenarios and realistic behavior for other agents. Okay, so we have multi-agent behavior here. This paper incorporates another paper which is called Wayformer. It's part of the research that has been going on, and the idea of Wayformer is related to Waymax. So it's kind of like, think of it, Wayformer is part of the Waymax stack, and the idea is which is really what we've been talking about in many contexts recently, the paper that came out of Berkeley in terms of video generation as part of robot learning. So it's all in that category. What we're trying to do here is really have a simulator that can take scenes, real world scenes captured by Waymo or others, and they have a big data set for that. Waymo has a big data set for data that has been captured in the wild, and then from there generate more scenarios, generate all kinds of scenarios. Maybe that's the idea, right? So there's a couple of things in the stack. For example, there is Wayformer, which is based on MODAR, which takes LiDAR data detects objects and then tries to predict their motion. If you think about the fundamental problem that autonomous driving technology is facing here, is one is object detection, and then classifying objects in moving or not moving, which is part of the Waymax stack. And then you have to, once those that can move, you want to be able to predict. So what that means, okay, if I have a house in front of me, I don't need to waste my time thinking about whether that my house might move or not. So the probability of that house moving is zero. Well, it's not really zero. You could have a Monte Carlo simulation where that house actually breaks down in an earthquake, but let's not go there now. Let's keep sort of in the sort of the more realistic scenarios. The house is not going to move, but there's a pedestrian that might move. So there's a couple of things that Waymo has been working on in this field. So one is like this waveformer, which is using motion forecasting for 3D object detection in point cloud sequences. So this comes, you have LiDAR, you generate a point cloud, and now you do motion detection. There's motion diffuser, controllable multi-agent motion prediction using diffusion. So think about this like we've seen this, Shuren Song does that. So we're using diffusion to generate potential paths of agents. This, of course, relies on a massive amount of data that is available to train this. But the idea, then we have MODAR, which is, goes back to waveformers, so using motion forecasting for 3D objects in point cloud. I just discussed this. I think in general, what they're trying to do, there's a paper that he discussed where they use key points, human key points, and then from there infer pedestrian shapes and then how they move. Think about it like if you want to represent a human, you don't need all the pixels or all the point clouds in a human. What you really need is only sort of the knees, the elbows, the edges of the human, because that's enough information. So this goes back to also the compute budget and the memory budget, which is always part of the equation. So I think if I go through the research here again, it's really Waymax is kind of the culmination of a lot of this research, which is, okay, how can we represent the scene? How can we generate data for simulation, and then how can we actually use that? And then we have also the sim to real problem, which he hasn't been talking about too much. I think when it comes to future projects, which is, I think, really interesting, the future projects are kind of in the realm of large language models. So for example, we have video language models that could be used for auto labeling, which is part of the general problem that autonomous driving infrastructure has been confronted with. Auto labeling, we've seen that from Tesla also. And the way auto labeling could be used with video language models is you could just have scenes and then label them, right? Use video labeling, and I think that is part of what Waymo's doing. There's certainly a huge opportunity on that front. Think about it. Like you could see, have very semantic understanding of scenes, particularly out of distribution scenes, such as there's a policeman waving, standing in the middle of the road waving, right? This is something that an agent might not be able to recognize. An agent might stop because they think there's a pedestrian in the middle of the road, but because it's a policeman waving, semantically, the model could understand, actually, I can actually drive and pass by that person. So we have scene description formats. So we have whatever currently is being used to describe scenes and describe scenarios. And then we have the sort of large language model format. So we have this multimodal models, if you will, and certainly we've spoken about this a lot. So Waymo's on that path, and I think there's some infrastructure work to be done. There's some data layer type of work to be done. How do you let's say, do you vectorize everything and just concatenate, or do you keep language information, semantic information different from pixel information? Do you turn pixel information into language? those sort of questions. There is a comment by Vlad. He says, we would like to enable chain of thought. Chain of thought, the idea of chain of thought is that you can sort of connect locally unrelated points. So chain of thought in the large language model space means that you can, through prompting, help the model generalize better because it might have been trained on data. So for example, we have, we're buying groceries in a grocery store. So buying groceries, strawberries, apples, milk, all that belongs to a grocery store. But then we have, I also need to park in front of the grocery store. That's not directly related to fruit. So a chain of thought could help sort of bridge that gap by having, I am parking because I'm going to a grocery store. So then there's a connection between the groceries, the strawberries, and the actual parking. So maybe the model could infer that if you buy ice cream, you might want to park closer, those sort of things. So chain of thought in the autonomous driving scenario, I guess makes a lot of sense because you could have all kinds of scenarios where data has been trained on I see again, let's say the policeman in the middle of the road waving, that's possible, but then the policeman in the middle of the road waving to somebody else to run over and help him because there's somebody injured, that is maybe a context that is not necessarily have been trained, and then chain of thought could help. Well, she is waving to somebody and has an injured person on the road. So the large language models could infer, well, maybe they want another person to run over the street. So maybe you as a car, you should slow down. So those are the kinds of semantic ideas that I think Vlad is talking about. He wasn't very specific. This was a 55-minute talk. So certainly, to pack all the Waymo research into that is pretty good. So he did a good job, but nevertheless, I had to go back and read a lot of the papers that Waymo published, and also just read about him and look at YouTube and all that stuff to get a better sense for what they're really doing, right? Follow human instructions. So that's another one where we could have maybe also an agent that you could drive. Imagine a scenario where you drive and you tell the agent, hey, what, turn left. I don't want you to go right. That to me is tricky because of the voice recognition problem. So I'm not so sure about that. So I would have to dig a little bit deeper, and then definitely preserve LLM and VLM capabilities with limited compute budget. So this goes back to the model distillation problem, where we have a compression of models that might actually be useful for edge devices such as cars, and who knows. I'm going to talk about Vladan Koltun in a different setting, but I think Vladan's work with drones that he presented recently at MIT is super interesting. I've also attended that presentation online. So I'm going to talk about this separately. I don't want to mix it here. Or maybe I should mix it. I'm not sure. Maybe I should mix it. Maybe I should just introduce Vladan's work here too. Why don't I do that? So I'm going to introduce Vladan's work here too and talk about that because it's related. But before I go to Vladan, I guess to summarize Dragomir's work, again, this is general research at Waymo, which is, I would say, the meat of the bone is detection and motion planning. And then using various sensors, in particular LiDAR. Waymo's certainly making a big bet on LiDAR. And then we have Waymax as sort of the combination of everything into a simulator for motion planning and motion detection, motion planning, and realistic generation of traffic scenarios. We have model distillation, auto-labeling infrastructure, and then fundamentally what Waymo is doing is definitely trying to incorporate transformer technology into the self-driving car space. Now let's talk about Vladan Koltun. He's currently with Apple. He's a researcher. I think his roots are back at Stanford. And he talks about this drone project. And I think it's really interesting because there's a lot of interesting corollaries between Vladan's work and Drago's work. Not just that their accents are similar, but also like they're working with autonomous agents. They're working with decision-making in a nonlinear space. So you can't really use control theory, supervised learning. All these things don't work very well. Reinforcement learning works a lot better in a autonomous driving setting because we have, or the combination between imitation learning and reinforcement learning probably is the best path forward. Imitation learning is great. You can learn probably 80% of driving through imitation learning. The 20% out of distribution stuff needs to be learned through reinforcement learning. I think that's almost, maybe somebody can prove that, because these are nonlinear functions that need to be optimized. In other words, you have too much randomness and unpredictability in the path and the trajectories, and the best way to solve that is through reinforcement learning. Whether it's model-based, not model-based, offline, online, those are questions that haven't been answered properly, and I think simulation, in my opinion, has the potential to solve that problem. Within simulation, we could have online model-free reinforcement learning, which I think is the most general way of reinforcement learning. So you just learn on the job and keep learning. I mean, it's the same with humans. The best way to learn is on the job, and I think Vladan talks about this in the drone presentation, that simulation is crucial for drones, because otherwise you would just destroy them all the time. If you did online off model-free and reinforcement learning, it means you don't know nothing and you just keep trying, right? So I think the best way to do that would be in sim. So that's what they did. The project has been published in several publications. They've done a competition in Zurich with Davide Scaramuzza, professor at the University of Zurich in robotics. And I think fundamentally this project is, it's kind of like, according to Vladan, it is sort of the AlphaGo moment for robotics. So think of it like, look, who cares about drones racing in gates, right? But it's a proof of concept, and in particular, it's an reinforcement learning algorithm. That's the key. So they're using reinforcement learning. It's model-free and on policy. So deep reinforcement learning, model-free, on policy. Let me unpack that. First, let's talk model-free. So they're not using any kind of model of the world. So this is not, let's say, pre-trained on imitation learning or anything like that. There's no experts that this has been trained on. So this model-free, it's on policy. So that means the policy is being updated as we speak, as the trial and error goes on. And it's deep reinforcement learning. So the planning function is parameterized with parameter set data, and it's being updated. It updates the policy in real time. So this is the setting. Now, I don't know the actual intricacies. They're using PPO, which is an optimization algorithm that helps optimize a deep reinforcement learning algorithm. It starts with a certain policy, and then it updates based on what's called an advantage function. So I think in a nutshell, what this is trying to do is really trying to find, you have, let's say, you're in state T1 and you have action T1 in state T1. And if you take that action T1 versus action T1 prime, action A1 and versus action A1 prime, then going forward, how can you maximize your reward? And then you go to the next, let's say you use A1 prime because you have better reward, and you keep going. The reward function maximizes two things. One is racing to the next gate with a perception objective that rewards keeping the next gate in the field. So this agent is optimized for keeping the next gate in the field and then racing through that gate as fast as possible. This is the reward function. And you see already the intricacies of deep reinforcement learning here. Maybe this is not the best reward function, but in this case, it worked out. They won. They were much better than humans and all of that. So this seemed to be the right reward function. But Vladan actually doesn't spend too much time on the reward function itself. This would be a very good question. Like what type of have you been experimenting with reward function design here, and what should be done? Interesting also in the talk, he mentions that there's no interaction with the other opponent. So the way this racing works, I believe it's kind of like surfing where you race against another one. So there's always a one-on-one race. So there's also, it's not just an absolute race, how fast can I go through these gates, kind of like ski racing, but it's more like you race against somebody else. So it's not an absolute race, but a relative race against somebody else. So there's probably some strategies there too. And Vladan says that they didn't really think about multi-agent behavior. They just race as fast as they can. And he mentioned that it might have been actually beneficial, maybe, to have a third reward here, which is something like keep the other opponent a certain distance away from you, but you don't necessarily have to go super fast, because then the risk of failure is also high. You could hit the gate and things like that. So I think, why is this really exciting? I think I do agree with Vladan. I mean, this is super exciting in many ways. What these people have to do is really find low compute and memory budget type solutions. That's first. I mean, they can't have an H100 on this thing, so there's definitely some edge compute. They use Jetson, I think, some NVIDIA edge compute devices, but there's definitely some interesting stuff going on there. I think we have a model that needs to be distilled down. So we have the model distillation problem from before, from Drago's talk, and I think here the same. I mean, you can't have this massive models. If you, let's say, you could use some transformer-based technology, but you have to distill. They didn't use that, but I'm just saying, you have some issues here with perception models. I guess you need to use state space models for perception. You can't use transformers or visual transformer, any of that. It's just too big. So you have to be very efficient. But I think what's really most interesting to me personally is really the deep reinforcement learning part, because I believe that this approach, by the way, okay, I'm sorry I didn't mention, but the most fundamental thing here is that what they did is they trained this in sim, and then they used some very few trajectories in reality to adjust for the sim to real discrepancies. Sim to real discrepancies happen through dynamics such as, physics, turbulences, air resistance, things like that, and then also perception problems, like there's some blurring going on with perception in the real world versus in sim. So the way they solve this is they record onboard sensory observations from the robot together with a highly accurate pose estimation from a motion capture system while the drone is racing through the track. Motion capture system is, I believe it has to do with, like, you can very precisely detect where the drone is at any point in time and have a sort of trajectory planning algorithm running the drone sort of semi-autonomously, but then you can learn from that trajectory and adjust your reinforcement learning parameters, so then the drone can autonomously fly without this motion capture system. Vlad talks about motion capture system because motion capture system really solves for vision. Like, once you know where the drone is and you have a trajectory, then it's all about speed and reaction. So think about, like, imagine you know where you have to go, like you've solved for vision. So this is a bit like, let's say, a ski racer, like, you see, like, the vision is not the problem here. It's just simply reaction, technique, things like that. So that's kind of what they're doing here. They're just adjusting the technique, if you will, and not dealing with the vision side of things, and then adjusting once the parameters are adjusted, then you let the drone out in the wild, and then it's able to fly through. So to summarize, I think Vladan's presentation incredibly inspiring. I think he talks about a silent revolution. Whether he tries to make a big deal out of it or not doesn't really matter to me. I think it's an interesting project. It's an interesting problem to be solved. It was solved, and let's go from there. I think it relates to Drago's presentation because both of these projects, both of these ideas are sort of in the same realm. We have embodied decision-making agents that have to move in the real world. What kind of models can we use? In the case of Drago, they're using transformer-based technology. I mean, they have a lot more compute and memory budget. They can do that. or that's at least the goal. They want to combine large language models, visual language models with existing motion planning, trajectory detection, multi-agent planning, all those things. Versus on the Vladan side here, it's a drone. There's a lot less compute memory budget, so you have to be a lot more efficient. They're using a model-free, on-policy, deep reinforcement learning algorithm, which is no model, no world model, on policy or just policy on the fly through trial and error, and you have a deep reinforcement learning decision-making function that approximates what the drone should be doing. This contrasts to, let's say, Tesla. They want to build a world model, so they have this, and I think also Waymo. So in the autonomous driving space, that's not the case, at least for now. Now we could kind of bridge the gap and say, well, if we could have fully simulated driving scenarios, then that is the world model, and then you just learn based on that, and then you don't really need another kind of model within the model or whatever. You just use you have the world model, which is your sim. You have an on-policy deep reinforcement learning algorithm that learns how to drive, and then you deploy it in the real world. We're still away from that, but I think Waymax is one step towards that. I don't know where Tesla stands. Tesla has kind of a world model too, in a sense that they have hundreds of thousands of people who drive, so they could use that and bootstrap themselves into some sort of either transformer-based technology or something along those lines that generalizes enough, that has enough distribution of potential scenarios, so you can then learn from there and then fine-tune. So there's these hybrid approaches, but I think the reason I picked those two events for this week is they really are crucial for our endeavor here at Orange Capital Partners. We are highly invested in embodied decision-making agents, particularly through Tesla, but also through NVIDIA. And we believe that there is a huge opportunity on that front to generate wealth, but also change a lot of things in the real world to the better, which has always been our sort of overarching goal. Is not just to generate wealth. It is just generate wealth in a sustainable way, and that can only be done if the world can take advantage of all these technologies that we're invested in. If you will, Peter Thiel's P times Q. The Q is the value you create for the world, has to be incredibly high, and then P is the value that you capture from that has to be high too, so you can then generate wealth. Thank you.